All throughout the universe, different types of signals propagate. Some of them, like sound waves, require a medium to travel through. Others, like light or gravitational waves, are perfectly content to traverse the vacuum of space, seemingly defying the need for a medium altogether. Irrespective of how they do it, all of these signals can be detected from the effects they have on all the matter and energy that they interact with, both along their journey through space all the way up until their eventual arrival at their final destination. But is it truly possible for waves to travel through the vacuum of space itself, without any need for a medium to propagate through it all? For some of us, this is a very counterintuitive notion, as the notion of things existing within and moving through some form of empty nothingness just doesn't make any sense. But plenty of things in physics don't make intuitive sense, as it isn't up to humans to tell nature what does and doesn't make sense. Instead, all we can do is ask the universe questions about itself through experiment, observation, and measurement, and follow nature's answers to the best conclusions we can draw. Although there's no way to disprove the ethers, or anything else that's unobservable, existence, we can certainly look at the evidence and allow it to take us wherever it will. Back in the earliest days of science, before Newton, going back hundreds or even thousands of years, we only had large-scale, macroscopic phenomena to investigate. The waves we observed came in many different varieties, including the ripples that wind caused in clothes on a clothesline or on a ship's sails, water waves on the sea, ocean, or lake, the waves that propagated through the ground during an earthquake, the waves that emerged in a tight string that was plucked, struck, or oscillated, or even sound waves, whose effects could be felt differently in air, water, or through solid land. In the case of all of these waves, matter is involved. That matter provides a medium for these waves to travel through, and as the medium either compresses and rarefies in the direction of propagation, a longitudinal wave, or oscillates perpendicular to the direction of propagation, a transverse wave, the signal is transported from one location to another. As we began to investigate waves more carefully, a third type began to emerge. In addition to longitudinal and transverse waves, a type of wave where each of the particles involved underwent motion in a circular path, a surface wave, was discovered. The rippling characteristics of water, which were previously thought to be either longitudinal or transverse waves exclusively, were shown to also contain the surface wave component. All three of these types of waves are examples of mechanical waves, which is where some type of energy is transported from one location to another through a material, matter-based medium. A wave that travels through a spring, a slinky, water, the earth, a string, or even the air, all require an impetus for creating some initial displacement from equilibrium, and then the wave carries that energy through a medium toward its destination. It makes sense, then, that as we discovered new types of waves, we'd assume they had similar properties to the classes of waves we already knew about. Even before Newton, the ether was the name given to the void of space, where the planets and other celestial objects resided. Tycho Brahe's famous 1588 work, De Mundi Aetheri Recentioribus Phenomenis, literally translates as on recent phenomena in the ethereal world. The ether, it was assumed, was the medium inherent to space that all objects, from comets to planets to starlight itself, traveled through. Whether light was a wave or a corpuscle, though, was a point of contention for many centuries. Newton claimed it was a corpuscle, while Christian Huygens, his contemporary, claimed it was a wave. The issue wasn't decided until the 19th century, where experiments with light unambiguously revealed its wave-like nature. With modern quantum physics, we now know it behaves like a particle also, but its wave-like nature cannot be denied. This was further borne out as we began to understand the nature of electricity and magnetism. Experiments that accelerated charged particles not only showed that they were affected by magnetic fields, but that when you bent a charged particle with a magnetic field, it radiated light. theoretical developments showed that light itself was an electromagnetic wave that propagated at a finite, large, but calculable velocity, today known as c, the speed of light in a vacuum. If light was an electromagnetic wave, and all waves required a medium to travel through, and, as all the heavenly bodies traveled through the medium of space, then surely that medium itself, the ether, was the medium that light traveled through. The biggest question remaining, then, was to determine what properties the ether itself possessed. One of the most important points about what the ether couldn't be was figured out by Maxwell himself, who was the first to derive the electromagnetic nature of light waves. In an 1874 letter to Lewis Campbell, he wrote, "It may also be worth knowing that the ether cannot be molecular. If it were, it would be a gas, and a pint of it would have the same properties as regards heat, etc., as a pint of air, except that it would not be so heavy." In other words, whatever the ether was, or more accurately, whatever it was that electromagnetic waves propagated through, it could not have many of the traditional properties that other, matter-based media possessed. It could not be composed of individual particles. It could not contain heat. It could not be a conduit for the transfer of energy through it. In fact, just about the only thing left that the ether was allowed to do was serve as a background medium for things that were known to travel but didn't otherwise seem to require a medium, like light, to actually travel through. All of this led to the most important experiment for detecting the ether: the Michelson-Morley experiment. If ether really were a medium for light to travel through, then the Earth should be passing through the ether as it rotated on its axis and revolved around the Sun. Even though we only revolve at a speed of around 30 kilometers per second, that's a substantial fraction, about 0.01% of the speed of light. With a sensitive enough interferometer, if light were a wave traveling through this medium, we should detect a shift in light's interference pattern dependent on the angle the interferometer made with our direction of motion. Michelson alone tried to measure this effect in 1881, but his results were inconclusive. 6 years later, with Morley, they reached sensitivities that were just 1/40th the magnitude of the expected signal. Their experiment, however, yielded a null result. There was no evidence for the ether at all. Ether enthusiasts contorted themselves in knots attempting to explain this null result. Perhaps the ether was being dragged by objects traveling through space, such as the Earth, and that's why a null result was obtained. Perhaps there is a stationary, motionless ether, and as objects moved through it, they experienced length contraction and time dilation, explaining the null result, and maybe, just possibly, the same ether that light traveled through, whatever it was, allowed for the propagation of Newton's gravitational force as well. All of these possibilities, despite their arbitrary constants and parameters, were seriously considered right up until Einstein's relativity came along. Once the realization came about that the laws of physics should be, and in fact were, the same for all observers in all frames of reference, the idea of an absolute frame of reference, which the ether absolutely was no longer necessary or tenable. What all of this means is that the laws of physics don't require the existence of an ether, they work just fine without one. Today, with our modern understanding of not just special relativity but also general relativity, which incorporates gravitation, we recognize that both electromagnetic waves and gravitational waves don't require any sort of medium to travel through at all. The vacuum of space, devoid of any material entity, is enough all on its own. This doesn't mean, however, that we've disproven the existence of the ether. All we've proven, and indeed all we're capable of proving, is that if there is an ether, it has no properties that are detectable by any experiment we're capable of performing. It doesn't affect the motion of light or gravitational waves through it, not under any physical circumstances, which is equivalent to stating that everything we observe is consistent with its non-existence. If something has no observable, measurable effects on our universe in any way, shape or form, even in principle, we consider that thing to be physically non-existent. But the fact that there's nothing pointing to the existence of the ether doesn't mean we fully understand what empty space, or the quantum vacuum, actually is. In fact, there are a whole slew of unanswered, open questions about exactly that topic plaguing the field today. Why does empty space still have a non-zero amount of energy, dark energy, or a cosmological constant, intrinsic to it? If space is discrete at some level, does that imply a preferred frame of reference, where that discrete size is maximized under the rules of relativity? Can light or gravitational waves exist without space to travel through, and does that mean there is some type of propagation medium, after all? As Carl Sagan famously said, absence of evidence is not evidence of absence. We have no proof that the ether exists, but can never prove the negative. That no ether exists. All we can demonstrate, and have demonstrated, is that if the ether exists, it has no properties that affect the matter and radiation that we actually do observe, and so the burden isn't on those looking to disprove its existence. The burden of proof is on those who favor the ether, to provide evidence that it truly is real.